This is starting chapter 12, or 13 if you're in the new book, and we are looking at graphs of multivariable functions. So this is 12.1. First of all, we've seen this little chart before, and since we're starting a new type of function called a multivariable function, or sometimes function of several variables, I'd like to go back and quickly review what we already know about this chart, and then we're going to add a little bit of new information. So again, all of your math up to this point, up to calculus 3, you were working with real valued functions of one variable, with one input, typically x, and one output, typically y. In the last chapter, chapter 11, we were working with vector valued functions of one variable. We still had one input, typically we use t, but now we have several outputs. If it was a two-dimensional vector valued function, our outputs might be two components, like x and y, or if it was a three-dimensional situation, we might have had three components, so three outputs, an x, a y, and a z. Graphically, it doesn't make sense to have 4 or 5 or 6 components, but algebraically, you could actually have 4 or 5 or 6 outputs if you wanted to. You just couldn't graph them anymore. I will add that one last little bit of information, sneak it in here. The graphs on all of these were simply curves, right? You know that if you graph a function in one variable, you get some sort of a curve, right? Maybe a parabola or a square root function or whatever. And we saw that when we graphed these, we also got curves. Might have been a two-dimensional curve. It might have been what we were calling a space curve. 3 dimensions, right? But the graphs on these are just curves. Here's our new type of function here in chapter 12. Actually, this is going to be 12 and 13. We're going to be looking at these real valued functions of several variables. And here are a couple of examples of the notation. This one, notice, has two inputs, x and y. You apply the function, and you get a single output, z. So 2, for example, x and y, but leading just to the one output, in this case, z. We could also have 3 inputs, like we do here. X, y, and z in this case. But we still lead to just one output. In that one, I've called it w. So a real valued function of several variables is going to have several inputs, 2, 3, or it could be even more, but just one output every single time. So it's kind of the reverse of this, right? Instead of one in and several out, now we have several in and just one out. We'll see this chart one last time in chapter 14. We're going to add one more type of function. You can probably guess what it's going to be in terms of inputs and outputs, but we'll get to that in chapter 14. All right, my first quick example here, simply a matter of using a function of several variables. In this case, I have a function of 2 variables, f of x and y. Defined this way, we're simply supposed to find f of 4, 3 and interpret what that may mean in the context of a graph. So first of all, plugging in the values is simple enough. I just put 4 for x and 3 for y. And evaluating that, what would I get? 16 plus 36 minus 9. It's going to give me 52 minus 9, 43 for an output. What is that telling us? Well, keep in mind, just like in the typical situation where you're used to like a function of one variable, the input's the x, the output's a y, and then that creates an ordered pair on a graph. Same idea here. the input xy combined with the output, which I can interpret as a z, leads to a point on a three-dimensional graph. So what this is really saying is the point 4, 3, 43 is on the graph of this function. Now, we haven't really talked about what the graphs of these functions are going to look like yet. So right now, that's a question mark. We'll be talking a lot more about that in the course of this section. But whatever that graph looks like, we would know that that point would have to be on it. All right, we're going to start by looking at one specific type of graph. Some of these things graph as planes, and we'll be looking at that for a while, and then we'll generalize to other types of graphs of functions of several variables as well. So, for the next few examples, we will concentrate on planes as graphs of multivariable functions. So, I want to ask the question, what would the equation of a plane actually look like? And we'll start by thinking a little bit about the geometry. Suppose I know one point, P, which is coordinates x0, y0, z0, and is contained within my plane. So I'm going to call this point right here P. It's x0, y0, z0. Let's further suppose that we also know a vector that's perpendicular to the plane. Perpendicular, we often use the word normal, right? So the normal vector or perpendicular vector to that plane, I'm going to call that n, and we'll suppose that that has coordinates a, b, and c. So this n vector is the vector ABC, and it is perpendicular to the plane. My goal is going to be to figure out an equation for the set of a general or all points, x, y, z, that are contained in the plane. So this point over here just represents kind of a random point in the plane. You could have put it anywhere, it doesn't matter. This is just my general point, x, y, z. And my goal is to get an equation containing x, y, and z that defines the set of all the points, x, y, z in the plane. In order to do this, I'm going to create a new vector. I'm going to create this vector here that runs from my starting point to the general point, x, y, z. And I'm going to notice that since n is perpendicular to the entire plane, these two vectors must be perpendicular as well. So let's see, let's give that vector a name. Try to remember, I don't think I have anything specific. We'll just call this vector v for now. We know that n is perpendicular to v. And based on what we learned in the last chapter, we know that the dot product of perpendicular vectors must be 0. So since these are perpendicular, I can already say that n dot v has to be equal to 0. Let's write that equation out in a little bit more detail. N we called ABC, and that vector v, I can get that using sort of the standard approach of subtracting terminal point minus initial point. So x minus x naught, y minus y naught, and z minus z naught would be a way of representing that v vector. And again, I know that dot product must equal 0. I'm going to use my standard method for finding dot product, multiplying the first components, a times x minus x naught, plus the second components, b times y minus y naught, plus those third components, c times z minus z naught, must equal 0. This equation right here is called the point normal form of the equation of a plane, because to form it, you need a point, x naught, y naught, z naught, and you need the normal vector, a, b, c. Once we have actual values for these, we'll be able to multiply this out and get a little bit simpler form. But this is usually where you're going to start when you want to find the equation of a plane. That is stated in a little bit more formal way over here on the second page. To find the equation of a plane, you need a normal vector and a point, and there's that point normal form. All right, we'll do an example, and once we've done it, we'll talk a little bit more about another form of the equation of a plane called the standard form. But we're going to need to have some numbers to plug in before we can get there. So here in example 1 says find the equation of the plane through 2, 2, 0 with the normal vector n, 2, 4, 3. And it says to graph it. I'm actually going to hold off on graphing it for now. We're going to take a look at a graph in Maple a little bit later on. So here we go. Here's my point. So this is x naught, y naught, z naught. And here's my normal vector. So that's a, b, and c. I'm just going to plug all that into my equation. 2 times x minus 2 plus b is 4 times y minus 2 plus the c, which is 3, times z minus 0 equals 0. I'm going to multiply that all out. And I'm going to keep the variables over here on the left side. 2x plus 4y plus 3z. And then I'm going to take the 8 and the 4, move them over to the other side, so that would equal 12. And that's how I would write my final answer, my standard form for the equation of a plane. Will always look like this. X's, y's, and z's over here on the left equal to a constant on the right. And you know what? I think I've actually changed my mind about graphing. We are going to go ahead and graph this thing the best we can. By hand, I just want to show you what that looks like. As I said, we'll look at a Maple graph later on. If you ever need to try to represent a plane by hand, it's almost impossible to kind of give a general graph. Since a plane goes on forever, you'd eventually end up with just kind of almost like coloring this whole thing in. So what we usually do is we usually go for it in terms of the intercepts on the 3 axes. If you imagine the x-intercept, if y and z were both 0, x would be 6, right? 2x is 12, x is 6. So I can put 1, 2, 3, 4, 5, 6 on the x-axis as my x-intercept. Same idea over here on the y-axis. If I want the y-intercept, x and z would both be 0, and it looks like y is going to end up being 3. And then finally the z-intercept with x and y being 0 is going to be z equals 4. If you kind of play connect the dots with these 3 points, like so, what I actually have, this little triangle looking thing, is just the piece of the plane that lies in this case in the first octant, right? You can imagine this slanted plane kind of cutting through the first octant. It would go behind and below all of these planes. It would keep on going forever. But this is just the part I would see just in the first octant. These 3 lines that we just drew actually have names as well. This line here that sits in the YZ plane is called the YZ trace. This would be the XY trace. And that would be the XZ trace. So by graphing the intercepts of each axis and the traces, you can at least get a little bit of a feel for kind of how that plane is slanted as it cuts through space in our three-space graph. All right, let's try a few more. You know that 2 points determines a line. 3 points will determine a plane. So in our next example, I've given us 3 points, and I'd like to find the equation of the plane that goes through those 3 points. Now remember, to find the equation of a plane, you need a point and a normal vector. So I'm going to start by just kind of drawing sort of a random diagram of those 3 points. I'm not going to make any effort to get them into an actual correct space. Instead, I'm just going to sort of put them all 3 here on my paper. And I'm going to start by picking one point that's going to be the point for my point normal form. And I'm just going to pick P. So I'm going to say P is my X naught, Y naught, Z naught. Now, I need to get a normal vector. If I were to create 2 vectors here, PR and PQ, those vectors lie within the plane whose equation I'm trying to find. I want a vector perpendicular to that plane, so it has to be perpendicular to both the vectors I just drew. And we know a way to find a vector perpendicular to 2 known vectors. We use the cross product, right? So I'm going to say if I want my normal vector, n could be found by doing the cross product of PR and PQ. All right, let's see. PR, if I just subtract terminal minus initial, would be 4. Negative 2 minus 4, negative 6. Negative 4. I'm going to cross that with PQ. Again, terminal minus initial is negative 4. Negative 3, 1. So I'm just going to do that cross product real quick. And that's going to give me negative 6i plus 16j minus 12k. And I got to subtract 24k plus 12i plus 4j. So I end up with negative 18 for my first component. Negative 12, 16 minus 4. No, positive 12, sorry. 16 minus 4 would be positive 12 for the second, and negative 36 for the third. Now remember that I don't really care what the length of my normal vector is. All I care about is its direction. So I'm going to notice these are all divisible by 6. I could just go ahead and divide this whole thing by 6 or even negative 6 if I want more positive values. And I'll still have a perfectly good normal vector since I won't have changed its direction, just its length. So just as an illustration, I'm going to say let's divide by negative 6 and say 3, negative 2, 6 would be a perfectly good normal vector. And that's what I'm going to use as my A, B, and C. So ultimately, here's my X naught, Y naught, Z naught, and there's my ABC. All right, from here on out, it's basically just plugging them into that point normal form again. So I've got A, just 3, times x minus the 1. B is negative 2, times y minus the 4. And C is 6, times z minus 0. Do a little bit of algebra here. And I'd like you to get in the habit of just giving your answers in standard form. So 3x minus 2y plus 6z would be, let's see, that's 5, so negative 5. All right, let's take a look at finding equations for a couple more planes. Next one, I want the equation of the plane through this point. So there's my x naught, y naught, z naught. And I want it to be perpendicular to this line. So let's just think about the geometry for a minute. I've got my point P here, which is good. I always need a point. And then I also have this line R that I know is perpendicular to my plane. I need to somehow get a normal vector out of that line. And if you think about the direction vector for that line, which we can see easily is 2, 5, negative 1, the direction vector for the line is going to be perpendicular to the plane. So I can use it as the normal vector. So sometimes it's just a matter of thinking through the geometry. So that can be used then as my A, B, and C. And that means that I can put together my point normal form, 2 times x plus 4, plus 5 times y minus 0, minus 1 times z minus 2, equals 0. A little bit of algebra. And I get 2x plus 5y minus z equals, that'll be 10, so negative 10 when I put it on the other side. All right, I've got one more kind of like this to do. I want the equation of the plane through a given point, so that's great, and then parallel to a given plane. Right, this is a plane. So let's again think about the geometry here. The plane I want contains my point P. I also know the equation of a parallel plane. So if this plane is the plane negative 3x plus 7y minus z equals 4, it's parallel to my known plane. I have a point in my known plane, but I need a normal vector. How am I going to get it? Well, I think I can pretty easily figure out the normal vector here. Because the normal vector just ends up being the multipliers on the A, the B, and the C, right? Look back up here for just a second. Right, my ABC, my 2, 5, negative 1. Once we do the multiplication, just ends up as the coefficients, A, B, C, in the final answer. So if I just pick out these coefficients, -3, 7, -1, those values have to be the A, B, and C from my normal vector. If that normal vector is perpendicular to my given plane, that same normal vector, again, vectors are free, right, could just be translated down there, and it's still going to be perpendicular to the parallel plane. Since I haven't changed its direction by translating it or moving it to the parallel plane. So I think I got my A, B, and C right there. So let's see, let's just organize the information. My point gives me the x naught, y naught, z naught, and that normal vector gives me the A, B, and C. So my plane is going to be -3 times x minus 5 plus 7 times y plus 4 minus 1 times z minus 2 equals 0. Multiply everything out. And I end up with -3x plus 7y minus z equals 30, 45, so -45. So last two problems, kind of the moral of the story there, a little sketch so you can kind of view the geometry can be really helpful. All right, got one more plane example for us. This time it's a little bit different. I want to find the line of intersection for the two given planes. Imagine, if you will, two sheets of paper. If you kind of brought them in as angles, right, and let them come together, they would come together in this line of intersection. And that's what I'm looking for. We're going to do this algebraically, but then I'm also going to just show you a maple graph to sort of help you visualize it as well. So first of all, how do I find the line of intersection? Well, for a line, I need a point and I need a direction vector. I'm actually going to start by saying if I knew 2 points, I could get everything I need. So I'm going to start by finding 2 points. So sort of step 1, find 2 points on the line. Now I know there's infinitely many points on that line. I just need to find any 2. So what I'm going to do is I'm going to choose a couple of x values. Nothing special about x. You can choose anything you want. But I'm just going to choose a couple of x values and figure out the y's and z's that go with them. You could have chosen y's or chosen z's. That's completely up to you. So I'm going to start by saying, let's start by choosing x equals 0. If x is 0, the first equation just becomes 2y minus z equals 1. And the second equation just becomes y plus z equals 1. And now I've got 2 equations and 2 unknowns that I can solve. As a matter of fact, these are set up to eliminate the z's perfectly. So that gives me y equals 2/3. And you can see right in here, if y is 2/3, z would have to be 1/3. So my first point is 0, 2/3, 1/3. All right, let's do it again. Let's choose x equals 1 this time. If x is 1, I have 1 plus 2y minus z equals 1. And I have 1 plus y plus z. equals 1. I can subtract off the 1's, so I have 2y minus z equals 0, and y plus z equals 0. Again, this one just happens to be set up so the z's eliminate perfectly. Sometimes you have to work a little bit harder to get that elimination, but I know you all know how to do that back from algebra. So this time I'm going to get 3y equals 0. So y equals 0. And if y is 0, z is also 0. So my point is 1, 0, 0. All right, I'm ready to find the equation of my line. Once I have 2 points, that's not too tough, right? My direction vector, I can get just by subtracting the 2 points, maybe just call this P and this Q. And let's just do, doesn't matter, Q minus P. Doesn't really matter which direction the vector goes. Like you could have done P minus Q, doesn't make any difference. And let's see, if I do that, I'm going to get 1, negative 2/3, negative 1/3. Now, I don't love working with fractions if I don't absolutely have to. And remember, any multiple of the direction vector is still a direction vector. It's just a different length. It's still the same direction. So I'm going to choose to multiply by 3 here, just so I don't have to work with the fractions. So I could use 3, negative 2, negative 1 as my direction vector. I also have a choice between my 2 points, which one I'm going to use as my point for the line. I'm going to choose the one without the fractions. Q, which was 1, 0, 0. And then remember your line vector is t times the direction vector plus the point written as a vector. So my line could be written as 3t plus 1, negative 2t plus 0, and negative 1t plus 0. So that line should be the line of intersection between the 2 planes. All right, I'm going to go ahead and show you what I've got done here already in Maple. I've pre-written this so that I don't have to spend a lot of time typing on the video. This is a new kind of graphing. It'll actually be in your next Maple assignment. In order to graph these multivariable functions, like the planes, we need a new command. It's called implicit plot, but 3D. So you'll see right there, I've got not just an implicit plot, but a 3-dimensional implicit plot. And in the square brackets, I've got the equations of the 2 planes that we were working with, right? I've set my x, y, and z to negative 5 to 5, and I've chosen colors for my 2 planes, green and blue, and they are graphed right there. One of the things that Maple does automatically is it kind of shows a whole grid pattern scattered over your surfaces, in this case your planes. There's a couple things you can do if you don't love that. Sometimes it can get hard to see because it's really dark. One thing you can do is you can decrease the number of grid points. It's called num points. And if I just set that to 100, notice that there are far fewer points and the grid's a little looser. I'm going to rotate this for you so you can see it a little bit. Well, there's those 2 planes. You can clearly see it does intersect in a line. If you don't want the grid points at all, you can set the style to be surface, and that's going to completely eliminate the grid points. So whatever you like, but again, if the graph's really dark because of all the grid lines, reduce the number of points if you don't want as many grid lines, or just change it to a surface. All right. Down here, I've graphed the line that we found. Remember, that's a space curve. So there's that line that we just found, the line of intersection, 3t plus 1, negative 2t, and minus t. Graph that in red. And then because these are two different types of graphs, right? One's an implicit plot 3D, the other is a space curve. To graph two different types of graphs on the same axes, we have to use the display command. So down here, I have a display command. My space curve here is first. My implicit plot is second. And those are, notice, are in curly braces inside my display command. I've done the num points thing here. We could change it to style if we wanted to. But you see these two planes, and now you can see that red line of intersection going right through that intersection of the two planes. All right, we are going to stop here for this particular one, and we'll come back and look at a couple of other types of graphs of multivariable functions in the next couple of videos.